morning. I am Kanagavalli from Civil Department. Today topic sewers in wastewater engineering. So in this sewer, we are going to see design of sewers. The hydraulic design of sewers and drains means finding out their sections and gradients is generally carried out on the same lines as that of the water supply pipes. However, there are two major differences between characteristics of flows in sewers and water supply pipes. The sewage main particle is suspension, the heavier of which may settle down at the bottom of the sewers, and when the flow velocity reduces, resulting in the clogging of sewers. To avoid silting of sewers, it is necessary that the sewer pipes be laid at such a gradient as to generate self-cleansing velocities at different possible discharges. The sewer pipes carry sewage as gravity conduits and are therefore laid at a continuous gradient in the downward direction up to the outfall point, from where it will be lifted up, treated and disposed of. First, we see hydraulic formula. First one is chassis formula. We have to find velocity. The formula is V equal to C into square root of Ri, where V is the mean velocity, is meter per second. C is the chassis coefficient, is meter power 1 by 2 per second. R is the hydraulic radius, it is in water depth in meter. I is the bottom slope in meter. The C is very complex, constant, depends on size, shape and smoother roughness of the channel, the mean depth, etc. C can be calculated by using Basin's formula. Basin's formula, C equal to 157.6 divided by 1.81 plus K divided by R power 1 by 2, where K is Basin's constant, R is hydraulic radius. So based on inside nature of the sewer, the values, the K value is varies, depends on first one, very smooth, the K value is 0.109. Second, smooth bricks and concrete, the K value is 0.290. Third, smooth rubble masonry, the K value is 0.833. Third, good earthen material, K value is 1.540. Next, rough bricks and concrete, the K value is 0.500. Next, rough earthen material, K value is 3.170. Next, Manning's formula. The Manning's formula is V equal to K by N R power 2 by 3 S power 1 by 2. Okay, V is velocity of flow in meter per second. K conservation factor of 1.486. N Manning's coefficient. R hydraulic radius in meter. S slope of the water surface. The value of N is calculated by Kutter's formula. The Kutter's formula is C equal to K1 plus K2 by S plus K3 by N divided by 1 plus N power N by square root of R into K1 plus K2 by S, where C is chassis roughness coefficient, S is friction slope, R is hydraulic radius meter, N is Kutter's roughness, K1 constant 23 in SI unit, K2 constant 0.00155 in SI unit, K3 constant 1 in SI unit. So next, Eisen-William formula, that is V equal to K into C R power 0.63 S power 0.54, where V is velocity, K is conservation factor for the unit system, K 0.849 for SI units, C is the roughness coefficient, R is the hydraulic radius, S is the slope of the energy line. Next, Crimp and Burgess formula. That is V equal to, for calculating velocity, V equal to 83.47 R power 2 by 3 S power 1 by 2, where V velocity of flow, R hydraulic radius in meter, S slope of the water surface. When calculating minimum velocity, the flow velocity in the sewers should be such that the suspended materials in sewage do not get silted up. That is, the velocity should be such as to cause automatic self-cleansing effect. The generation of such a minimum self-cleansing velocity in the sewer at least once a day is important, because if certain deposition takes place and is not removed, it will obstruct free flow, causing further deposition and finally leading to the complete blocking of the sewer. Self-cleansing velocity. To calculate minimum velocity of flow, following formula is used. V equal to square root of 8K divided by F into ES minus E divided by EG into DS, where V minimum velocity of flow in meter per second, K size of solids in sewage varying between 0.06 mm, F DOS is coefficient of friction, normally 0.03 mm. ES specific gravity of solid material flowing in sewage varies between 1.2 to 2.65. E specific gravity of liquid in sewage generally 1. G gravitational acceleration continue. DS dia of solid particles in mm. Maximum velocity. The smooth interior surface of a sewer pipe gets surrounded due to continuous abrasion caused by the suspended solids present in sewage. It is therefore necessary to limit the maximum velocity in the sewer pipe. This limiting or non-scoring velocity will mainly depend upon the material of the sewer. Next, we see effects of flow variation on velocity in a sewer. Due to variation in discharge, the depth of flow varies, and hence the hydraulic mean depth varies. Due to the change in the hydraulic mean depth,